Victor and I have developed this demonstrably, and you know, we have other targets, but that's the first question. Well, it's part T. Wait. Sure, but it's not the way now. Don't have to use it. Also, you can't just call it T. Yeah, well, I mean, you have to expose what? You have to expose it first. So that's what I'm saying. Yeah. Yeah, I was supposed to say. I mean, we're still. Yes, we're halfway through. Yeah. Yeah. Well, we're not charged to do that in law. Oh. We're not going to. I don't think anyone officially actually, so you just watch it. Well, I mean, I have a question, right? I just that this it's a couple of have in different places. Firewall crossing. Well, I mean, you said yes. There's a lot of questions. You mean am I probing my local firewall? Oh. So you want to induce the client to send it. So I want to. Do you need a? Well, I need. I don't need. It just needs to complete the. So I mean, don't you just set up?
Okay, let's get started. Thank you, Stuart. All right, welcome to the CCWG meeting at IETF 126. This meeting is being recorded. Make sure that you've joined the Meet Echo via the QR codes that are on the microphones, by the door, linked in the IETF agenda. Make sure that you've actually joined that. That's part of how we keep track of who is here. It's also how you're going to enter the queue when you want to say something. This is the IETF note well. Please take special note to read it. Make sure that you pay extra close attention to your IPR obligations as somebody who's participating in an IETF event. This working group also operates underneath a code of conduct. So if you observe any code of conduct violations, you can reach out to the chairs, the ADs, or the ombuds team. These are some helpful links for the PDF that you can click on later. And this is our agenda for today. So we're gonna kick off with some hackathon updates, and then we'll talk about our working group documents, and then we've got a couple other proposals to talk through with some time for discussion for each one. Before we do that, would anybody like to bash the agenda? And would anybody like to volunteer to be a note taker? It's pretty easy these days, given our amount of AI-generated summaries and transcripts and recordings. Yes, thank you very much, Stuart. All right. First up, we have Mohit. Let's talk about some hackathon updates. You'll have a clicker in a second.
Thanks, Eric. Hello, everyone. I'm Mohit, and with me, I have one of my students here in person, Abhyode. We had another student join us remotely, and we participated in the hackathon over this weekend. So, we are here just to give a small update on what was the work that we were able to do it. So initially we had a couple more objectives, but then the time frame of the hackathon was shortened. So we also revised our objectives. We had three objectives, out of which two of them were to evaluate FQ and FQPy in different scenarios, Wi-Fi scenarios, one with a mobile hotspot and one with the Wi-Fi access point. And besides that, before we came for this IETF meeting, we actually completed the integration of Pico Quick library with NS3, but there wasn't sufficient time for us to do all the necessary testing. So during this weekend, we spent time on doing different tests of the integration that we have done with Pico Quick and NS3. And happy to share that in the time frame that we had, we were able to achieve all these three objectives. I'll invite Abhyuday to give you a detailed update on each one of these objectives, and then I'll come back and tell also what we were able to achieve after the last ITF meeting that we had done.
So hi everyone, very good afternoon. I'm Abhyuday, undergrad at NITK School, and this is my first time at IETF. So a little update on the hackathon, starting with the performance evaluation of FQPy and FQCodel. So we did the performance evaluation on two separate devices. The first one is going to be a mobile hotspot. So as you can see, the topology over there, we had a client, which in this case is my laptop that you can see, the silver color one. Now that was connected to the mobile hotspot, and the mobile hotspot was in turn connected to the IETF access point, which is connected to the IETF backbone. And now that is finally going to be connected to the NetPerf EU buffer growth server. Now, what tests did we run? We ran a couple of Flint tests that included RRUL and TCP and down tests for a different number of streams. And what did we notice? So these are a couple of graphs that we were able to plot. Before that, my bad. So as you can see, the FQPy and FQCodel algorithms were put in the egress queues of the mobile hotspots. So the mobile has two separate interfaces, one for the hotspot and one for connecting it to the access point. So in both of these, we tested with different QDISC algorithms. And yeah, so these were the plots, some of the plots that we obtained of RRUL and 200 and 100 TCP download ones. Next, so the QQIW235 is an access point, and this runs on OpenWRT, which already has FQPy support. Again, the client, which in case my laptop is connected to this, which had FQPy and FQCodel running separately, and then it was connected to the PoE switch of IETF. And these were again a couple of graphs that we plotted. So what did we infer from these? One thing that we consistently noticed from these was that the tail latency of FQPy is better than that of FQCodel. Now, the orange line that you can see over there is that of FQPy, and the blue line is of FQCodel. So if you notice the graphs, the orange line ends pretty early compared to the blue one. So that is one inference that we made. But yeah, we have to run a couple of more iterations to conclude on that. One more thing that we observed was that if you can see on the left bottom corner, you have the box plots. Now, as you can see, the jitter of FQPy, the one on the right, is comparatively lesser than the FQCodel one on the left. But still, if you look at the median one, they perform almost very similar to one another. So we have to spend more time on that and look into how it differs. Yes, the other thing is the integration of PicoQuick with NS3. So we observed that NS3 doesn't have any quick topology simulator in it. So for that, instead of implementing Quick from scratch or something, we took PicoQuick, which is a well-known C implementation of Quick by Christian Yutema. And we built wrappers on top of that so that network researchers would be able to simulate quick topologies using NS3. Yep. So these were some of the things that we did. The QR code over there can be scanned to access the source code of it, and we'd be happy to receive feedback on it. Yeah. Thank you.
Thanks, Abhyuday. So this work of integrating PicoQuick and NS3 comes out of the fact that in the last couple of IETF meetings, when we were working on the hackathon and interacting with members from CCWG, we saw there was a lot of interest in simulating Quick on NS3, particularly for congestion control algorithm evaluation. But like Abhyuday said, NS3 does not have a native model of Quick, and to build something natively in NS3 will take a lot of time, and we already have so many nice Quick libraries available out openly. So we picked up just to get started with PicoQuick, and we integrated it successfully. There are a bunch of examples that we have added. One another thing is that PicoQuick also supports multipath Quick. So we already added an example for multipath Quick simulations in NS3. And the snapshot that you see here is just to show an output of one of the examples where we have one congestion control algorithm as C4 and another as cubic. These are only some initial steps that we have provided, but the code is openly available and it can be modified for your own use cases or for the congestion control algorithms that PicoQuick supports. So PicoQuick has a bunch of congestion control algorithms. Apart from the work that we did at Hackathon, I'd just like to also brief about a few things that are related to CCWG. These are the things that we got it done after the IETF 125. So we submitted a patch to FreeBSD to align a small bit of things of PRR with 9937. And I would like to thank Richard and Michael for merging that PR that just got merged on the day of the hackathon. We had submitted it a couple of months back, and this was the first contribution from our team to FreeBSD. So it was a great experience. We have also built two models, one model for LEDBAT++ and another model for R-LEDBAT, and the merge requests are already open on the NS3 mainline repo. LEDBAT++ has already received a lot of review. It should be soon getting merged in about a couple of weeks. We still need feedback on R-LEDBAT. Would like to encourage the community to take a look at the code if you are working on those algorithms and would like to give us some feedback. We also did one another interesting thing after the last IETF. Flint is a very popular tool to do the buffer bloat test. But if you would like to repeat those tests with NS3, you do not have that supported. So we have built a native Flint-like application in NS3, which will easily reproduce whatever you do on a real Flint tool. You can exactly simulate that in NS3 with the same RRUL specification and same TCP upload and download specification. Finally, we also have some new topology helpers in our Nest tool that will allow you to easily spin off the topologies for congestion control evaluation. That's it from our side. And thank you for this opportunity to share the updates. Any feedback or any input or any questions?
Raffaello, University of Aberdeen. Thank you so much for putting PicoQuick into NS3. I think is an important achievement. So I was thinking, like, okay, my PicoQuick is going to evolve. Quick is going to evolve. Is going to change. How difficult is to maintain? How difficult is if a new version of PicoQuick come up to introduce them?
Right. So we have ensured that the PicoQuick evolution and NS3 evolution will not interfere with each other. The wrappers are pretty independent of both the things. So unless there is a significant update in either of those tools, you don't really need to worry about its maintenance. So the wrapper is very thin wrapper that we have built. It's a very tiny little code that sits into the contrib directory of NS3. And both can evolve independently and still be able to operate with each other. As I said, unless PicoQuick decides to change its APIs in a significant manner, we don't need to worry about the maintenance part of it. Do you want to add something?
Yeah. So only if the certain API call, if the API signatures are changed, then we have to do some change in our part of the module. Else, if there is any internal change in PicoQuick, then it's going to be all good.
Alessandro Ghedini, Cloudflare. Thank you for sharing this. If you could just briefly, like, what's the
effort required to say add new implementation to like alternative to PicoQuick to NS3? Is it just a matter of like implementing the same sort of modules with like whatever API someone wants, or do you need like an actual like command line sort of tool to do the?
So this wrapper that we have built, what we did is after we did the PicoQuick integration, we also were interested to do the MS Quick integration. But the way MS Quick is built is, I think it uses, it's a multi-threaded library as opposed to PicoQuick, which is a single-threaded library. And there were some challenges when we were trying to integrate it. But this effort took us quite some time. It took us about 2 months, but it shouldn't take a lot of effort if the structures of the Quick libraries are almost similar. But it would largely depend on what's the Quick library doing internally.
So does it require the library to do all the I/O, sending packets and receiving packets, or can it just like pass the data?
It just pass the data.
Okay.
Yeah.
Thank you.
All right. Thank you. Yeah. Thank you.
Okay. Thank you very much. It is delightful to see Quick integrated into NS3 here. And I think one of the things that we talked about a lot when we were first starting CCWG was how can we as a community help move things forwards? And this is a huge part of that. So extra thank you. Next up, we have a very small number of slides from Greg to talk about another hackathon thing. And then we will hop on with the rest of our agenda.
Right. Yes. Thank you. So I did a quick version of this presentation earlier today in TSPWG. So these are the same slides. We did have another iteration of the L4S interop at the hackathon this past weekend. This has been a great opportunity for congestion control developers to test their implementations, both with, in some cases in the past, real network bottlenecks, as well as in more recent iterations here at IETF, using a Linux box as a bottleneck. And also testing their implementations, sharing that bottleneck with other congestion control implementations. This time, again, it was a shortened hackathon this time. The link to the summary slides is there, so feel free to take a look at some of the results we got. Highlights would be continued testing of the Scream integration with libwebRTC, continued testing of the Netflix NDTC congestion controller, some testing with the Apple responsiveness tool and its L4S mode. And we had intentions to test a alternative network configuration for L4S support called SRM, which is a draft being considered in TSPWG, and also to test the latest version of iPerf2, which has a nice Android client that can be used to test different L4S functionalities. If anyone's interested in participating in a future interop, be it the next IETF in San Francisco. Also, we host a series of interop events at Cable Labs with cable network equipment and OLTs, et cetera, that support L4S. So let me know if you have questions. All right, thanks.
Thank you very much. All right. Thank you, Greg. And next up, we have our first working group document to talk about. Ian. Let's talk about BBR.
Great, thank you. So I will go through some of the changes that have happened since we last discussed. Then we can talk about next steps afterwards. You've probably all seen these before, but there's some links to various implementations and draft on GitHub. So there have been some notable changes in the most recent draft. A lot of them are just kind of referencing things like ACK frequency and ACK receive timestamps as requested, just to understand like how those are relevant to BBR potentially. There's some kind of missing variables and other kind of like efforts to make the pseudocode match up with the actual like text. In some cases, there was normative text that was missing. Not a major issue in the scheme of things. You could kind of figure out what was going on, but it was definitely less explicit than it could be. Neil did a fair amount of work trying to improve the undo definitions. So if you are, particularly in TCP, some of the undo logic is fairly complicated. So if you were implementing this in TCP in particular, take a look. And I have assertions from Neil after asking him about this, that indeed fixing this and making sure all the undo logic is correct does actually create real world performance improvements, at least for the workloads he's tested it. So it is not merely a theoretical exercise. The extra complexity apparently does translate to real world application benefits. I of course asked this because it is somewhat complex. The most notable addition, and we have a few slides on it, is the precautionary bandwidth probing text. Hopefully after I run through it in slides, if you go back and read the text, it will be nice and clear. This is one of those cases where I think a picture is very helpful. We finally landed the PR that I wrote previously, adding some test cases for BBR. All it does is kind of describe, I think, about 15 test cases that you might want to write and approximately what should happen. It doesn't attempt to go into a ton of depth, but at least if you were going to write a series of test cases, it gives you kind of like a starting point of like, here are ones you almost certainly should have, just to sanity check that like your implementation doesn't have any obvious issues. And it does have things, test cases including application limited behavior, so on and so forth. Yeah. We removed BBR from a bunch of methods that had it for no obvious reason because it's the BBR draft. I think you probably know it's BBR. Just made the methods long and some other editorial improvements. And yeah, so for the most part, these changes are refinements, and the cautionary probing is probably the only change that is more than just like more clearly explaining what the algorithm is. So I'll go into that. It's a little bit high. I guess I should be taller. So the goal here is to reduce queue pressure and packet loss. So in particular, the observation is that after you've observed excess packet loss because you've probed up, for example, and you've set in-flight long-term to a value based on probing up and probing too high and getting excess lost, the next time you enter probe up, the suggestion is to probe very carefully and kind of like stick your toe in the water, colloquially, and then immediately pull it back. And if your toe burns off, then you probably shouldn't keep probing. And so you wait a round trip and, see if your packet got lost or if there's any loss in that round trip. And then you kind of go back into the probe up phase once you're certain that like, putting your toe in the water sort of exercise was safe. And yeah, this again came out of Neil's experience, I think commonly in data center networks, but not exclusively, where there really was like a max in-flight that was sustainable on the path, and going even a little bit over that, like immediately caused loss. And so, the normal probe up behavior would kind of keep probing up for like a bit and also have a sustained in-flight above the in-flight long-term, causing more loss, as well as like if you were competing with other flows, a fair amount more loss to other flows. So there's a few ways of thinking about it, but yes, you're kind of getting to the in-flight long-term. Actually, I'm going to go to the next slide because I think it's easier to see it. Great. I love the picture. So in our, I don't have a pointer, do I? That's okay. If you see that second loss, that's the point at which in-flight long-term has been set. As you see that little dotted line at the top for in-flight long-term. When we go back into probe up, which is the second to rightmost little light purple square that says probe up, probe BBW up. We're only going to go to in-flight long-term, and the moment we hit it, we're going to probe down and drain the queue, and then go back into refill and probe up if by the time we exit probe down, we haven't encountered any loss. So if we, basically that gives us a confirmation that going back to in-flight long-term is no longer dangerous. And that's the goal here. And remember, there are a number of ways you can exit probe up. It's not just by hitting the in-flight long-term and having excess loss. You can also hit it just by not seeing any extra bandwidth. That causes you to exit probe up. So there might be a number of flows where this new logic kind of never comes into play, particularly if it's a more heavily buffered network. Um, so as a note, this is implemented, actually, next slide. Yes. Actually, did it say? Okay, experience, yes. This was in both TCP Linux BBR v2 and v3 since 2019 in the open source code, not in the Linux kernel. And so there was actually a fair amount of experience with it. And when Neil was just kind of doing a full read of the draft, he noticed that it was not actually in the draft. It has not been implemented in either ours or the move fast quick implementations, but that should be doable in relatively short order. This has only landed, I think, 4 weeks ago or something. So, that's just a matter of time. So certainly by next IETF and hopefully sooner, we will have that implemented. In terms of the implementations, I know Neil has been doing some work on upstreaming BBR3, v3 in Linux. So, and again, trying to get the draft and the code aligned. In Google Quiche, I actually kind of did an entire rewrite of v3 kind of based on the v2 code, but like trying to simplify it, remove some obsolete experiments, as well as just making the code a little bit easier to read. That is mostly done. It is missing a few features from v3 that were in the draft, and it is also missing precautionary bandwidth probing. So it is not quite done. But the idea is to have like more of a full rewrite rather than just keep evolving the code from the v2 code. And move fast also is fairly up to date. There are 2 notes about like differences from the draft that have kind of been there for a while. And also it lacks the precautionary bandwidth probing. So this is a relatively new issue, which is that there's, previously we discussed changing the probe RTT interval to 10 seconds from 5 seconds. I think Move Fast and Facebook had positive experience with this in terms of quality of experience for video playback, presumably because 10 seconds is long enough that you're almost always draining the pipe at least that often, so you avoid probe RTT being at a bad time for video playback. However, if we also have a 10-second window for min RTT, if we're not careful, we could expire our min RTT right around the time we enter probe RTT, and then that could inflate the target congestion window that we're trying to drain to. So, imagine if your min RTT, your long-term min RTT is 10 milliseconds, but like more recent RTT measurements are like 50 milliseconds, then suddenly like the amount of inflight you're trying to drain to is 5x higher than it was intended to be. So Neil noted this issue. He also noted that he's not sure he's actually seen this in production, but he is currently, I think, operating most production traffic with the 5-second threshold. Anyway, so we have 2 potential ways of mitigating this. We don't have a pull request for either, but if you have a strong opinion about which way to go, then let us know. But one is basically, make the filter a little bit longer to make sure it actually lasts to the end of the probe RTT interval, and the other one is just save the value entering probe RTT. So it's possible we will write up both in a PR because text is cheap these days with AI, and we'll just see what looks better. But if you have a strong preference or implementation experience, please let us know. And the next 2 issues are actually issues that have been open for a while, and I don't think there's anything new to discuss except to continue saying, like, if other people have implementation experience on either this or the next issue, they're definitely appreciated. But yes, I don't think there's actually anything new to discuss here. So unless people do have something new to contribute on either of these 2 issues, then I think that's it. Yes, so that's a summary. I have a question. Did folks understand the cautionary bandwidth probing algorithm, why it's there, what it does, approximately the mechanics? Yes? Okay. I think Neil is on as well if people have very detailed questions for Neil, who designed it.
Altanai first.
Hi, Altanai Komiraki. I've been following this draft from like the day one, but I don't understand the precautionary bandwidth is like a optimization, or is it, or somebody doesn't implement it, then they are not compliant with the BBR version 3. Is it optional or is it mandatory?
I think it's intended to be mandatory, although I say that with the caution that the TCP version implements it, the Linux TCP version implements it, and neither of the two quick ones currently do implement it. So, but I think the intent is that it's not optional. Does that sound correct, Neil?
Yeah, that was my intent, because it is a pretty significant improvement and in friendliness toward the the health of the queue and the RTT and loss rate experienced by other flows sharing the same bottleneck link. Yeah, and it's not, and it's a little bit extra mental complexity, but in terms of the code complexity, it's not actually too bad.
Got it. Thanks.
Thank you.
Yeah, Roland Bless, AIT. Just a clarification question. So this is just documenting what has been implemented 2023 or so?
Yeah, so this has been implemented in Linux since I think it says 2019.
Okay.
But it's not implemented in the two quick.
Yeah, because I mean, last year we did some measurements and they showed that BBR basically creates something like a BDP of Q, and just want to make sure that this was already then implemented, so it's nothing new in that sense.
Are we using the open source implementation or the upstream implementation? Okay. Because the upstream Linux implementation is 1, and the open source one is 2 and then 3, is my understanding.
No, you were using the BBR version 3 version.
Okay.
So, yeah, definitely. Yep. Thank you.
Cool.
Neil, I saw you joined and then left, but if you have a thing you want to say in the chat too, that's cool.
Yeah. That's all I have, unless you have anything you want to add, Eric. Okay. Thank you very much, everyone.
Thank you, Ian. Are there any folks who are currently implementing with or experimenting with BBR who have changed what they were doing since last time, would like to chat about it a little bit, had any questions that they ran into? Could we get a brief wave or thumbs up? I don't think we need like an official show of hands for folks who are actively involved in making some of this go. I know folks have spoken up in previous meetings, so I'm just curious, is there any updates there on that end? Wherein I nudge people to actually stand up and go to the mic. Alessandro, thank you.
Alessandro Godini, Cloudflare. So we've been working on and off on BBR some version for Quick. I feel like we're lagging behind like quite a bit at this point, but we've started enabling it more for some of our production traffic. It's still very much work in progress.
Thank you. Yeah, that's good to know. Anybody else? Cool. All right, feel free to chime in on the list as you run into questions or anything else too. I know there's a couple other folks who we've talked about offline or in various stages of implementing things or playing with implementations. So if you do run into questions or want to file GitHub issues, feel free to email the list, file an issue on GitHub, all that kind of stuff. Okay, next up, we have Scream v2. Magnus. For you.
Thank you. So I'm Magnus Westlund, here representing my co-authors, and Ingemar is nicely on vacation, so and he has done most of the development work. So, but it's I will do my best here. And if you run into a question, you will have to email them in worst case, but let's see what I can. So, Scream, real-time congestion control. And somebody reminders here about that we are using not the congestion window, but the reference window. And this is to enable us to send a bit more bytes in flights than what the congestion window have, and dealing with some of the video codecs, for examples, intraframe or other, to avoid queuing up too much data in the sending side. It's changing behavior depending on how long since we've seen congestion events. If longer, we can go into multiplicative increase, not only, and it's reduces based on both loss, ECNL for SC marks, as well as estimated queue delay increases. Using packet pacing at 150% of the target bit rate, and can increase it even further when it's uncongested. It's also integrating a lot of the integration with Scream is towards like a media rate controller for codec, etc. Here is some of the challenges, but for an implementation, but it's trying to ensure that you have it work on that side, hitting the target bit rates as quickly as possible to maintain the efficient interaction with congestion controller side. So let's see what's progress been done since 07 and to the current working group edition. One change has been to change this estimation deviation of the queue delay. It's gone to an average between the shortest and lowest, shortest and highest value, and using that average as to instead of the deviation, normalized deviation had before. And this is try to get a bit better robustness against clock drift, and also a little bit of scheduling nature. This, in its turn, it's used to affect the scaling of the reference window delay parameters, which affects the reference window's overhead, which is how much you can overdraft the reference window, and also controls the reference window growth. So it helps reducing the rate variations and queue delay. So, and means that we have adaptive so this adaptive reference window overhead actually gives us, we will see some simulation results on the next slide. So it restricts the bytes in flight when congested. When queue delay, the deviation by average is high. We get this reduction, and it allows bytes in flight to exceed the reference window more when we are uncongested. So let's look at this. On the left side, we have, if you have a static 1.0 scaling, and then on the right, we have if you have an average. As you can see here on the bit rate, it becomes more stable with this adaptive. And it also keeps the queuing delay more controlled and not growing as spiky. So so. And this is, so at 5 seconds into this simulation, we drop from 10 megabit to 5 megabit. And then after 10 seconds, it increases again. So, and another example here is coming up on the next slide is around the trying to improve how it handles reference window undershoot. So when the bit rate drops suddenly, the queue buildup can result in that actually clocking parts, etc. anyway, and increased RTT anyway reduces the actual transmissions. So the reference window decrease doesn't need to be as hard as if the ACK bit rate is larger than the target bit rate. This is a bit harder to see, but if you're looking around that event at 5 seconds when the bitrate drops, on the right side, we don't drop as fast and you recover more quickly, which is why the queue delay after this is bouncing a little bit more up and down towards limit and probing around what's available based on the probing that queue delay, and then falling back and going at it again. So it just becomes more responsive here in these events. One other change is trying to improve the robustness to link layer, in another word, non-congestion related losses. So what's been implemented is that reference windows reduction upon when you have lost packets only happens if the average loss rate is above a loss rate threshold. Currently, the default is set to 1%, or if the queue delay is larger than queue delay targets, a quarter of the queue delay target. So if you're otherwise it's been very little indication of congestion, we don't reduce it in consider it a spurious loss. And this increases the robustness and also avoids excessive AQM related losses. And so this example we actually have is an example of a data limit case, because we have a link capacity of 100 megabits, and the media bit rate maximum is set to 10 megabits. So on the right, you see that we using those full 10 megabits, except a few cases where it's like drops down and there's enough packet losses to actually cause something. While on the left side, you see the spurious congestion law limits the bandwidth reduction. And this is for 0.5% of packet loss, random losses here applied. So we also have a comparison with and without L4S, and this is for a mobile link, simulated mobile link. Christian, is it on the previous slide, or should I just conclude on this? I will conclude on this slide, then you can. So, so this is showing that applying L4S gives much more stable low queuing delay. It's slightly lower bit rates, so Christian, go ahead.
Good morning. Yeah, regarding this business of data rate, I mean, how much loss rate is lost versus spurious things? It's largely a question of fairness as well. I know that many implementations do that. We certainly do that for C4 and for BBR and for even for Cubic. We could do it for Cubic, I mean. The consequence of that is that the rate determines competition, how the competition goes between concurring flows. So if one flows react, if the loss rate is observed to be on average 1%, another use 2%, another use 20%, we will have obviously some unfairness issues.
Yeah.
And I wonder whether the working group here should take that particular point and maybe prepare a draft about it, about how do we think about it, what we should do. The other thing that is important there is that take the example of L4S. L4S has this rule for competing between non-ECN and ECN flows that says that the drop rate of the non-competing non-ECN flows is basically the square of the marking rate of competing of ECN flows. That square equation is based on the old modeling of TCP, asymptotic behavior of TCP. And that equation assumes that each individual packet loss drives down the congestion window. Now, if we start, I mean, if we actually do what you're presenting here and what I am doing too, and what other people have been doing too, which is reasoning on average, reasoning rather than reasoning on individual losses, then all these formulas become obsolete. They're just wrong. And so I think the IETF should start a discussion about that and eventually come to a recommendation. It'd be nice if everybody converged to 2.25% or whatever it is we converge on. But I mean, the same thing. And it'd be nice also if we told that to the modeling communities and says, hey, you know, be careful what you assume. Okay, let me speak.
I'm not disagreeing. I think with at least it's worth thinking more about it, because I think you're right that it is a point of competition. So, Mirja?
Try the other one, yeah. There we go.
I just want to react to the L4S part. So like screen has L4S enabled by default. So if it sees an L4S marking, it will react differently. This is only for non-ECN or L4S enabled queues. But I agree on the point that BBR has the same, that they also have a loss threshold. So like using the same loss threshold is probably not a bad idea. And thinking about this in general terms is probably also a good idea.
Martin Duke, Google. I think Christian raises very interesting questions. I would love to see him or somebody else start to see that discussion. I wonder if the ECN marking thing is a problem, given that all this ignorance of loss is related to queuing delay increase, which is, or lack of queuing delay increase, which is exactly where you will see, you know, ECT, or rather CE marking when the queues start building. That's obviously not perfect, but I would hope that those particular equations would not be obsoleted by something like this. Thanks.
Well, in fact, there are.
That doesn't match my intuition, but you've almost certainly thought about this more than I have.
So yeah, I think we have to come back a little bit more onto this later on. And I think for the Scream have very much the L4S integrated, behaving very much like in some sense, it works both on the delay and the L4S targets, and basically what it does is it converts the delay into equivalent alpha factors for L4S when it's being affected by the delay. So, but yeah. We are at the phase where we need to start actually writing down a bit about the evaluation for Scream, according to the 9743. And one question here is should we document this in a separate document or in the appendix in the draft? Is your opinion on that? I think we also start to think, say, does everything need to be shown basically by simulation, practical evaluation, and how much can you show by theory? Where certain things based on the algorithm will tell you that, okay, this according to the algorithm, it fulfilled some of these criteria. So if you have input on that, please send something. Okay. Another aspect which Ingemar have been thinking a little bit is the question of detection of rate policies or remediation. There's an example algorithm in the draft, but policies are difficult to handle, so Should we just ignore this, or should we continue working on it? So, Neil?
Yeah, regarding policers, my suggestion would be from our experience with BBR, be to maybe try to take an approach where the general algorithm has a response to packet loss that leads to sort of acceptable behavior in the presence of policers, rather than going down the road of having an explicit detector or estimator for the presence of policers and then having a specific policer response. And this is sort of based on our experience with BBR, where in version 1, we did invest a fair amount of time going down that road of sort of explicitly trying to detect the presence of a policer and then having a specific response for that. And I think, we did get to an algorithm that we felt worked pretty well in practice, but there was a fair amount of complexity. And at the end of the day, we decided after BBR V1, when we were moving on to V2, that we wanted to get rid of that detector to sort of simplify the code. So that would be kind of my advice there, would be to not go down that road.
Very much appreciate that feedback. So, yeah. Another aspect is, which we're looking forward here, is Google people are helping us with a WebRTC evaluation of Scream for L4S. It's ongoing. Hopefully see some results later this year from this evaluation, and it will hopefully be very enlightening to see how well it's working in the larger field test. Yep.
So Gary Fairhurst, I was going to try and speak to RFC 9743.
Yeah.
I see Martin's at the back as well, so I don't know what Martin thinks. So my personal opinion when we wrote that was we were trying to capture stuff that had to be documented somewhere in the IETF process. That might be via ICCRG technical talks, or it might be via papers, or it could be in a document. I don't think I ever saw each congestion control document having like some great big annex that was describing this. So probably I was thinking of a separate document. Whether that's published or not, I don't even know, because it was more to make sure there's coverage and understanding, because there's some pretty tricky design stuff going on here, and we all know that. Somehow we have to get good confidence. So that was my take. I didn't see Martin run to the mic, so I guess he can comment differently if he feels like it. Does that help?
Yeah, it sounds. It's up.
First of all, administrative note: if you choose to leave, you can leave by that door that is on my right. Eric's left. That one actually closes, which is probably good, or closes itself. So I agree with Gory that we do not have to have pages and pages of text in the specification discussing the 9743 evaluation, nor do we need to publish some other RFC that has all that stuff in it. I think just having a report in the minutes of in the materials of the working group for internal purposes is perfectly fine. Is evaluation necessary for all cases? I do know this is targeted for experimental, which is good in terms of maybe not having to. It depends what you mean by evaluation. So this is.
I think that was part of my question. Is like, it's one thing to write down, say, okay, our algorithm has the following properties in this condition, which this question answers. Just write down that it should never happen to be worse or behave different than that because of these following factors. Or if you actually needed a simulation for this use case, a particular case, to show that, yes, it's actually fulfilling those properties that the RFC specifies.
So if I understand correctly, the applicability of this this algorithm is global deployment of the internet for application limited flows.
Yes.
Okay. So to the extent, I think there's some language there about that not application limited flows. I think you can soft pedal the evaluation of that because people shouldn't do that. the gold standard obviously is data from internet-wide deployments. For internet scale effects, for scenarios that are not well captured in the internet but are important, like satellite stuff and so on, you probably have to do simulations. The 9743 does not preclude making kind of assertions, I guess, that based on some logical things. People can accept that or not accept that. That's the we have to decide. If you can at least do simulations of the cases that are applicable, of the use cases that are applicable to this algorithm, that would be ideal. Well, not ideal. Data is ideal, but it's probably sufficient.
Yeah. Okay. Thank you, Stuart.
I'm Stuart Cheshire from Apple. I came up to the microphone because the subject of polices has come up a couple of times, and I would agree that I don't think it's productive to try to put special code in to do something special for polices. Polices exist for one purpose, which is something in the network wants to tell the sender what speed it should be sending, and the only tool they have to do that is packet loss. And if you don't lose packets, that means go faster, and if you lose a packet, that means go slower. It's a simple binary signal. I don't like polices because they're very insidious. When you have a queue, the queue length grows, and you can, in principle, you can infer from the increasing round trip delay that you're going too fast, and you can back off before you lose packets, because losing packets is bad, because then you have to retransmit. Retransmitting adds delay. So problem with polices is you get no warning that you're exceeding your quota until suddenly it loses a packet, and you have no way to anticipate that and avoid it, which seems a little bit unfair. I do hold out hope that one day we'll see polices that use ECN, because that's a way to give the desired feedback to the sender about its rate adjustments without forcing it to retransmit. I don't know if there's any hope of that on the horizon, but let's shoot for that as our goal. Polices that use ECN rather than trying to work around today's polices.
Okay, thank you. We also have some consideration if we should make screen more conservative when L4S is not enabled, or no L4S in congested nodes. But yeah, we'll have to see if we get some results or considerations for that. So I think that is all that's planned to present. So unless there's some other questions, I'm done.
Thank you, sir. Next up, we're going to move into search. And I think, Jay, you wanted to share your own screen. Yeah. That's not now.
Hi, this is Jay. I'm happy to provide the update on the search algorithm. Search stands for slow start exit at right choke point. Okay, so in this update, we are going to provide the update for two things. One is the slow start exit signal analysis. This is respond to Milia's question, why should we use the good bit or basically the good bit rather than the RTT increment, and therefore we did some analysis on the signal strength and stuff like that. So we're going to give the update on that. And the next thing is we added the search draining phase to lower the queue upon slow start exit. So we'll provide the update on that too. Okay, so as everybody know, traditional TCP uses the loss detection or the ECN from the active queue management supported routers as a signal to exit slow start. And typically, especially for the losses, we have chance to overload. So in order to reduce that, researchers came up with mechanisms such as using a signal like RTT inflation from the base RTT, or monitor the delivery rate during the slow start, actually flatten out as a signal for congested router, the router getting congested, and we came up with those mechanisms. And the RTT inflation using that as a signal is more like high start and high start plus plus. And then delivery rate flatten out using that as a signal is either VBR or a surge. Okay, so it's not about the signal that we use, but it's the quality of the measurement that actually affects the performance of the slow start exit. And we don't want to exit too early because that's based on the wrong signal, because that is going to affect the performance during the slow start. So when we actually look at the RTT, RTT doesn't grow before it hits the congestion, and then it actually grows. Okay, and then if you look at the delivery rate as a signal, it exponentially grow, and then once it actually hit the congestion, then it flattens out. What about the noise in the measurement? So if you actually look at the noise in the measurement, the noise for RTT doesn't change before and after the congestion point. And this graph actually shows the noise in terms of the standard deviation of the RTT measurement. And for the delivery rate, what happens is based on the window size, irrespective of the window size to measure the delivery rate, what happens is as the pipe is actually getting filled up, as the pipe is actually getting filled up, what happens is the measurement get more accurate and accurate. So so basically nearby the congestion point, we have an accurate measurement of the rate. So in summary, RTT as a signal, the signal measurement quality improves when you actually hit the the congestion point, and for the delivery rate measurement, the quality actually increased before hitting the congestion point and maintain high quality. So this graph shows the measurement quality in terms of SNR, signal to noise ratio. So if you actually look at the SNR of normalized diff, which is the delivery rate, what happens is after the SNR goes to high before the BDP, and then once you actually hit the BDP, it actually goes up. And for if you look at the SNR for RTT inflation, in this particular one, we use the RTT of the last round minimum as the base. And then if you actually do that, the SNR actually fluctuate a lot because the using the RTT of the last round as a base RTT also introduced the noise.
Clarifying question?
I have a question, but you can feel free to go
Okay.
through more slides.
Yeah, please.
I'm happy to wait till the end, actually. It's fine.
No, I mean, basically, this is the end of the first topic. And this is basically, well, the one thing that I would like to actually, stress on this is, this is one of the reasons why, using the normalized difference of the delivery rate from the sending rate is actually a good signal to use for detecting slow start exit. Yeah,
Okay.
go ahead.
Correct. Ian Sweat, Google. Can you go back a slide?
Yeah. More?
Awesome. So, okay. So the bottom left is min RTT and the bottom, or sorry, windowed min RTT, and the bottom right is the normalized diff. Basically, it's the deviation from the expected bandwidth. Is that correct?
Right. So, I mean, this is actually send bytes and 1 RTT ago, how much I sent, and then basically, and now, which is 1 RTT later, how much was actually act.
Okay.
So,
and after the cutoff, after the point at which the dotted line, that's at the point at which, in theory, like you should be exiting slow start.
right.
Ideally.
So, exactly. So the red line, I forget to actually name it, is a BDP. Basically, when the the capacity is actually filled up.
And so the fact that that solid line is drifting above the
that means the quality is actually getting better because yeah, I mean, what this really means is this if you actually so if the send byte minus delivery byte is going to be converged to 0.5, and this is actually what you're seeing is going to 0.5, because in slow start you actually send 2 packets for 1 act received.
Okay. Okay. I'm just trying to understand the data.
Okay,
thanks.
got it.
I think I understand. Maybe.
All right, thank you.
So, Gori first, individual. I missed what you were actually measuring here. Are these compiled data from lots of internet paths? Are they a particular type of equipment path?
Oh, no. This is what the sender is actually measuring as part of the act coming back. Okay, so
what is the path?
Oh, the path. We actually, this particular one is actually the emulated network. We have done the same, the study for the real network like Wi-Fi, and also our company is doing the geo network. So we actually measure the same thing for the geo.
Do you have that data now? Can we see it?
I can actually provide the data if you want. I don't really have the data right now.
Okay, I'm not sure why we're seeing this in a working group if it's just an emulated path. But please continue and show us how the mechanism works, because I'm really interested in the mechanism.
Any more question on the first update?
Yes, I have a question. Altanaisis Komaraki. So you just mentioned that you are implementing this at the transport stack, correct? How would it matter if the app is itself restricting the outgoing packet? Like app is modifying app limited browser activity, for example. Will it throw your previous 2 new RTT measurements out of whack?
I didn't actually catch your question. So what was the question again?
Question is, if the browser's app is limiting its outgoing packets by itself, okay, the application is modifying the outgoing packets, will it not throw your network stack calculations out of whack?
Yeah, so you're talking about the app limited case, right? So yeah,
Yes.
in app limited cases, which is a lot of case in the network flow, the expectation is not exiting slow start. That's probably what's going to happen. So hopefully the search will not actually, kick the flow out of the slow start in that case.
Okay.
Does that answer your question?
Thanks. Yeah, that does. Thanks.
Okay. Okay.
Yes, regarding your comparison between, and that was the previous slide was nice, but that one, yes. These are the theoretical curves. What I'm worried about those curves is that the measurement of the data rate is depending on the measurement of the RTT.
That is true. However, the thing is, when you actually measure the goopit, right? I mean, irrespective of the measurement interval, basically slow start is actually pounding the network. It's adding a lot of packets to the network to actually congest the network. So when it actually goes to the capacity, if the throughput is actually go to the approaching the capacity, what happened is the measurement interval, whether it's actually aligned with the RTT or not aligned with the RTT, it doesn't really matter. But the throughput, measurement gets more accurate. That's the point that I would like to make.
Oh, yeah. Well, basically, slow start, wet measurement boils down to looking how many packets I sent in a given time and dividing by that time. The problem is that that time does include an RTT measurement. You can put it at the end, at the beginning, or whatever.
Yes.
And so the RTT jitter, which you are measuring as the uncertainty on the RTT, your minimum RTT discussion, also impacts the precision of the wet measurement. In fact, it impacts it a lot because it's on the divider.
That is true. However,
and so I mean, we have. I mean, I'm not saying that we should use one or the other. I'm saying we have to be very careful that wet measurement appears to be solid, but the hypothesis between that solidness, the hypothesis that one, of course, that the wet is constant, which it may or may not be, and the other hypothesis that the delay is constant, which is definitely not true in some Wi-Fi networks.
yeah, so I'm not really saying we should use either RTT or the delivery rate. I'm just trying to explain the property of those measurements. And basically, RTT is more like a one-dimensional measurement, and the delivery rate is actually combining two-dimensional measurement, like how much, when, right? And basically, and therefore, we can actually get more information about the network, I believe, by monitoring the delivery rate. For example, I'm
yes,
just saying.
I mean we agree on that. That's not a question. I mean,
Yeah,
but,
I mean,
but we have to be careful. But there is a lot of noise in the wet measurement that derives from the jitter in the RTT.
Yes, I agree with that. Yeah. But all I'm saying in this graph for the normalized diff, graph is that whether yeah, you're right. If the denominator is actually affected by the how much you have to go back, is determined by the RTT measurement, yeah, that's another source of error. However, when we actually do the measurement, actually, when it actually goes back, I mean, when it approaches the congestion point, even after a couple of rounds, I mean, it actually the measurement error is actually reducing there. So so basically, that's why it actually shows the smaller margin for the noise. Okay.
Okay. Thank you.
I think we have Neil.
Yeah, regarding the discussion of application limited flows, I believe you said hopefully search does not kick the flow out of slow start, but what is the actual mechanism that the algorithm uses to avoid premature exit of slow start for application limited flows?
Yeah, so I mean, that's more like a current work that we are actually doing. Probably, so the current thinking is to use the SNR. If the SNR is actually low, that means the signal, the measurement doesn't really, I cannot really trust my measurement too well. So in that case, we won't actually kick the flow out of the slow start. That's the mechanism that we are currently working on to use.
So can you give us some intuition about how that would work? So let's say, for example, that there's an application limited flow that sends 100 packets each round trip time, and the BDP is 200 packets. How does that keep us from exiting slow start prematurely?
Yeah, so the thing is, basically, if you actually have the sending rate and then receiving rate, most likely, if it's app limited, then basically receive rate and then sending rate at the RTT before is going to be equal. However, when we actually measure each of the bin, our current bin size is about 1/3 of the RTT. Basically, if you actually monitor, those bins. I mean, we don't really have enough bins to even make the search exit decision. And in that case, we are not going to make any decision about the slow start exit. If we have large enough packets, then basically what happened is we do have the enough bins to make a decision. But if you actually could calculate the standard deviation of the last two RTT, we don't really have a good confidence because the signal to noise ratio is going to be low in that case. Does it
Okay,
make
thanks.
sense? Okay, thank you. Okay, so the next one is actually a very quick one, I hope. Basically, we added the drain phase at the search exit point. That is. So the earlier version, let me just. So the earlier version, when we search detect the exit, then we actually set the SS threshold to the current congestion window at that time and exit it. However, that actually have the packets in the queue build up. So we wanted to actually clean that up. So what we are doing right now is we're trying to actually drain the excessive queue in the congested router. And that's by compute the target C window, because now we know what is the capacity. So we have the capacity is computed based on the 3 bins, which is 1 RTT, and we know the minimum RTT and all that information, so we can actually come up with a target C window. And therefore, and what we're doing is, we could actually set the congestion window, to that target window, but we don't do that. We slowly reduce the congestion window, like every three packet worth of bytes, we reduce by 1, and that was because a packet loss can actually happen after the search exit. In that case, we don't want to degrade the performance of fast retransmit, because fast retransmit, if you actually cut off too much, then there won't be enough congestion window size to do the fast retransmit. So in order to fix that, not to cause that, we were actually slowly draining the data. So for example, this one actually shows the one example run where the search exit was detected around 4 BDP. And basically the draining is and enter into the draining phase and exit once everything is actually getting drained. And at the time, it's handed off to the congestion avoidance. Okay, so basically, that's the update. And then the ongoing work right now is, since now we have this property that the signal to noise ratio is actually not that great in the initial start. What we can do is we can actually use that to determine what rate the C wind should grow, because there is no magic about like base to exponential. So if we have low signal to noise ratio, that means the path is actually not full. So basically, we could actually even grow faster. And then, when the signal to noise ratio is actually good, then basically we are approaching the congestion point. So we probably don't want to even do exponential base 2. So we could, like high star plus plus, we could, reduce the incremental rate. So more gradually. So that is basically things that we are looking into. Okay.
Martin Duke, Google, just a quick comment. I understand why you're picking 3 based on fast retransmit, and you have to start somewhere, and that's great. But don't over-index on it because, as you know, there's rack, there's all this other stuff.
Yep.
You know, you're gonna have to, as you generalize this, you're gonna need to have a more generalized approach. Thanks.
Got it. Thank you. Any other question? All right. Thank you.
Thank you. All right, we wanted to do a quick poll. So if you're not in the Meet Echo yet or paying attention to your device, now's a great time. So the first question is simply I have read a recent version or really any version of this document. So we just want to get a sense of kind of who's looked at the doc, who's read it. I know some folks have given some great feedback on the list, et cetera. So thank you to all the folks who've done that. And we'll leave this poll open for a little bit. And then we will have one more coming after it, which is asking about who has implemented or is planning to implement. But for right now, this is just, have you read it? Looks like that's almost settling. Oh, there we go. A couple more. I also sometimes have no opinion on whether or not I've read something. Or I forgot that I read it. That also counts. Okay, looks good. And next we have, I have implemented this or am interested in implementing this. I know there's some folks who've given some feedback on the list saying like, hey, I'd like to see how this compares to insert X other thing here, or I'd like to see these changes before I proceed with some of it. So this is both, I have implemented or interested in implementing, but also if I saw these changes, I would then be willing to implement. We had asked in a previous meeting about whether or not we think CCWG should be looking at slow start in general, and generally said we think we do. And we have a couple of different proposals. This is one of them. So that's what we're trying to get a sense of right now. Christian, I see you are in the queue.
My uneasiness with taking slow start as a subject is that I am not sure that, I think that the big problem we see addressed in search is a discrepancy between slow start and congestion avoidance. Is that once you exit slow start, especially on a high bandwidth delay product network, then congestion avoidance is really unresponsive. If suppose you're on a satellite network and you have divided your windows because of some loss or something, it'll take a very, very, very large number of RTTs before you gain back. And so that puts a premium in being really, really cautious about exiting slow start, because if you exit it too soon, then you will have consequences that go down on the connection. And I think that's a fundamentally bad design. Because, we have to assume that network conditions are going to change all the time. And so this design in which you do all your discovery during initial phase and never change it after that, or change it very, very slowly only after that, is fundamentally bad. And that's why I'm uneasy with this.
I think that makes sense. If I can say that back to you to make sure I understand it, you're essentially saying if we were able to be more responsive to conditions during congestion avoidance, we wouldn't care quite so much about where we exited slow start because we'd be able to fix it rapidly anyway.
Yes.
Yep. And I think there's also the point that there's a substantial percentage of connections that never exit slow start before they're over. And I know in the previous IETF, we saw some data suggesting some meaningful user wins from being better about how we get to the right rate.
Yep.
So both of those kind of go together, I think. All right, I think that's good for our polls. We're not asking again or anything for adoption for this particular document right here. So we will keep coordinating with the different authors of the different slow start proposals and kind of talk about that and give some updates to the group as we go. Next up, we have quick slow start evaluation at Mozilla. Oscar.
Can I make a comment about adoption?
You absolutely can.
I'm gratified to see that people are interested in implementing this. If we're talking about adoption, particularly as a standards track document, but
we are not, to be clear.
Okay, that's fair. Well, I think an interesting question to ask is anyone doing internet scale experiments with it? If we are going to, if we're considering going down that road. Cool. Thank you.
Convenient timing for this talk.
Yeah.
Also not an accident.
So yeah, if you look at those slides, hi, I'm Oscar from Firefox networking team. So we are actually doing internet scale experiments on this. And yeah, let's talk about that. Is this working?
Should be.
Ah, there it is. So yeah, in NeckU, which is Firefox's quick stack, we have recently implemented search and HiStart++ in kind of like a runtime switchable framework. Then in addition to what we already had as our default, which is just like the standard congestion event-based classic slow start. And so we've done some ABC experiments on this, on desktop nightly, on desktop beta, and now on desktop release, which ran from July 2nd to July 19th. So this is like very, very recent. And yeah, so now we bring some of the results, and we also bring some questions as to help with interpreting what we're seeing. So let's get into it. So this is actually kind of like the data set makeup. To the point that was already brought up, that like a lot of connections never exit slow start. Of course, this is the browser's perspective, so this might look slightly different for like CDN. But yeah, so out of all of our connections that are part of kind of this experiment, the vast majority never grew the congestion window at all, so app limited all throughout. And of the smaller part that did grow the congestion window, which is 8.61%, of those 8.61%, only 4.42% exited slow start, to just give this some kind of scale. And then if we look at those 4.42%, we see that it's actually a bit different for the heuristics we deployed. So search is exiting slow start slightly more often than HiStart++ and classic, with about like 0.5% more. And if we then look a bit further towards how many of those slow start exits are actually exited heuristically, so out of all the slow start exits in that cohort, how many are exited through the heuristic that runs on that cohort? So for classic, this is 0, as expected. And then for HiStart++, it's about 2.5%. For search, it's 12.6%. So a lot of the exits are actually based on congestion events. Of course, search here is better than HiStart, but this like both are fairly low percentages. And to make some sense out of that, let's like scale this back out of the experiment and look at kind of all of Firefox release, no heuristics running. And so this is our SS thresholds at slow start exit. And this is only for connections that actually did grow the congestion window. So if we do like one GET request that has some random loss, this is not included here. And so we see P50 is at 20K, P25 is at 14K, and P5 is actually at 8.6K, which means with IW10 that we saw congestion at the initial window, basically. And so all of this is, yeah, too early for any of those heuristics to work. And this kind of explains why we're seeing such low percentages. Now, let's actually look at kind of like how the heuristics perform, how it influences other measurements. So for packet loss, both in the 95th and the 99th percentile, we can see that search has lower packet loss ratio than high start has lower packet loss ratio than classic. And this is consistent on a day-by-day basis. So across both percentiles, search every day has the lowest packet loss ratio. And then if we go to the next one, which is upload throughput, we can see that this is kind of all over the place. And so there's no clear winner. So like one day search has the best upload throughput, one day it's high start, one day it's classic. So for our experiment, I think like upload throughput data is kind of inconclusive. Then from those high level metrics, if we look a bit lower, actually at the slow start exit point. So now we're looking at the exit slow start threshold, and we're looking at the percent difference to the classic cohort over all the percentiles. And if we look at the higher percentiles first, now it works, okay. Then we can see that search is often exiting with a slow start threshold higher than classic. And for that, we got to say that we did not implement this drain phase that Jay just talked about. So this is just search detected slow start exit, and we exited slow start. So yeah, search higher number in the upper percentiles, which is probably good. So it's after congestion, but before loss, and kind of inside of that, the congestion window where you detected, where you would experience the loss, and then that times 0.7 with us deploying cubic. So it's kind of in that range. And then for high start, it's actually a bit lower. So high start might be exiting prematurely there. And I see Martin maybe has a question for this slide.
Yeah, I'm trying to reconcile this with the higher heuristic rate for search. So does this mean that when high start is really, when high start kicks in its heuristic less often, when it does, it really kicks it in like at a rate that maybe is too low?
So I can't like perfectly answer that.
Sure.
But so yeah, my take is that obviously when it kicks in, that it is in those higher percentiles, because that's where we see an actual difference in the SS thresh. And it is lower than what the classic saw after reducing its congestion window by 0.7. So that's what the data says. The interpretation is kind of up for grabs. Yeah.
Thanks.
Antonio Klopler. But another possible explanation might actually be that you're exiting with search more often. Some of those might be incorrect early exits that might be inflating your higher percentiles. So comparing against the full distribution of like final windows may also be interesting.
Sorry, again, so what you're saying is search might have early exits, which would influence this, what we're seeing, what you're
Yeah,
looking
it might
at?
actually make the early, you actually see higher exit rate for search.
Yeah.
So that could actually mean that some cases that did not exit with the classic algorithm and the other one are exiting with search, and those windows are actually end up being larger for that reason.
Yeah, so I think that because this is by percentile, right? So anyways, we're looking at the higher SS thresh values here. And so for those higher SS thresh values, we see that they are at the same percentile higher for search than for classic. Yeah.
Matt Chores, Meta. Did you collect any information about the browser metrics besides just the connection metrics? Because it's kind of hard to reason about these in isolation. Because you had like a very noisy graph for P95 of like upload throughput, but since I was like, does this make any difference to page load time, HTTP requests, stuff like that, since it's kind of hard to see that this did anything other than it being kind of what it was supposed to do on the tin from the connection standpoint?
Yeah, so the problem with the browser metrics is that they are mostly about us as the browser downloading, right? In which case, that's not controlled by our congestion controller, but
Well,
by the servers.
requests are still sent out, right? So
yeah,
like,
right. But so I assume for a case where really we're just like sending some GET requests to then get a site, this will not show in this data anyways because we're filtering for only connections where we actually were not app limited.
I wouldn't assume that. So it'd be kind of interesting to see if, because like so when we've changed things about slow start, it does make an impact on things like GET requests and POST requests and page load and stuff like that. So even if you're just from the client side, but it would also be interesting, like the actual uploads themselves. So if those are large, knowing what the effect on that is would be interesting.
Yeah, I don't have that data right now. We can talk afterwards, and maybe we can look at something on the live dashboards. So yeah, then I'll pick it back up. And now if we actually look at the lower percentiles, then we will see that here in the lower percentiles, so with low SS thresh values, search is actually also seeing kind of like, there's a difference to the classic cohort, which means there are search exits with low SS thresh values. And so if we look into this, and this has been discussed just now, so our take with that was also that we think search kind of might be struggling with app-limited traffic patterns that we see in the browser. And so if we are not continuously sending, then this might break some of the assumptions that search makes. And it might then mess up kind of the byte tracking logic, which then is causing it to maybe exit early. And so, yeah, I think Jay presented some ideas on how they could mitigate this, and I would love to see that because I think for us, search was performing quite good in like the higher percentiles. But this for us would right now kind of be a blocker to just like deploying this as a default, because in the app limited cases, we shouldn't see exits, obviously.
I'm sorry, Antonio's question made me think that maybe I'm confused. That PDF is over connections that had a heuristic exit, or all exits from slow start?
This is over all exits from slow start.
Okay, so non-heuristic exit should be very much like the
so they should be the
be
same.
like classic, right?
Yeah, but so this is per experiment cohort. So we split the population in 3 cohorts running classic, search, or high start.
Okay.
And so my assumption before looking at this data, knowing that we see so many for classic, we see so many low congestion window, low SS thresh exits, my assumption would have been that basically for the lower percentiles, this should be one flat line, because all of those are from congestion events.
And the percentile scale is the size of the SS thresh?
Sorry, the central scale?
The x-axis.
So the x-axis are the percentiles, which would be the size of the SS thresh.
Okay.
And this is then the percent difference to classic.
Right. Okay. Thanks.
You're welcome. And so as I said, there's some problems with app limited traffic patterns, and also to that.
Yeah, hi. Thanks for doing the work. But I think I agree with Martin that at least some kind of time-based metric would actually be useful. I would propose just to look at like how long it takes until you exit slow start, normalized by the round trip time. So how many round trip time it takes to exit slow start. You should see a difference there as well.
Yeah, I think in retrospective that would be a practical metric to have, unfortunately fast. So our metrics are always aggregated, so we can't sort of look at stuff in retrospective. So if we wanted to measure that, then we would kind of have to redo the whole thing.
Yeah.
Yeah.
And like actually a time-based metric could also give you some information about the cases where you don't leave slow start, but you might still see an improvement.
Yeah, it's a good suggestion. Thanks. And yeah, so yeah, this is basically most of the content. So now I have some questions. Kind of, I would love to hear from others. Doesn't need to be now, but kind of if how your connection patterns, as in percent of never growing the congestion window, percent exiting slow start and stuff like that, how this is matching up with our experiences. And I would also love to hear opinions or takes on why we are seeing so many low SS thresh congestion events. It's sort of like sub 20 kbytes. For the last one, I'm gonna make a guess myself, sort of. So I have one theory, which is that we might be seeing actively managed queues. So the theory is that our bottleneck as the browser is the home router. And we do actually, over all of our release population, see that like 10 to 20% of our congestion events are caused by ECNCE, which means there must be some actively managed queues, otherwise we wouldn't be seeing CE markings. And so this maybe could mean that we see congestion events earlier, both the loss and the ECNCE kind, because we are operating on other buffers, kind of, and they are not the typically large buffers with tail drop. So yeah, that's a theory. I would love to hear your takes. And yeah, if you have any more questions, if you have any opinions on any of this, generally, we also have some more data, like this is kind of the tip of the iceberg. Then yeah, please find me, ask them now, or send me an email.
Jonathan, just from my own understanding, this
Quick
is stuff
comments.
sent by Firefox, right? So you'd expect that the vast majority of what you send is one or just a few get requests and then sit around waiting for the response, right? So
yes,
that
correct.
explains why most things never like exit slow start.
Yes, so that's very much the case. Like, and that's all of those connections probably that never grew their congestion window at all, and so we filtered them out. Yeah, I would also be very interested to know what other browser vendors maybe see if their stuff matches up with this. Yeah.
Kazuhok, firstly, I think the results that being reported here could be kind of skewed because it only looks at the connections that experience losses, which means that for the connections that had higher BDP, they are less likely to observe losses, unless you put very much pressure. So that means that you see more among all the connections being established by all the users. The connections that had lower BDP would appear more in these results, and that will skew the results. And in case of us, we only have data from the server side sending to the client. But if we compare the results that collect all the results above 200K versus 1 meg, the SS thresh distribution changes by twice or something. So the numbers that you are looking could be skewed due to that. And I think Matt made a good point arguing that probably looking at the TTFP, for example, or the time until upload completes might be a good metric, and I agree with that.
Yeah, I would also, like in retrospective, I would love to have something like time to last byte. But yeah, unfortunately, we didn't at the time think of that, yeah.
2 more quick comments.
Yeah, just to comment on seeing a lot of low SS threshold exits. Basically, I was in our network, I was actually fighting with that as well. And basically, one of the reasons that we actually seen, the low SS threshold exits are based on like active queue management actually not well configured for the network condition. Typically, the random early exit that uses that is actually very much depending upon like configuration, and it could be actually not well configured for the situation, in which case it actually cause the burst of packet errors, packet drops. Even if like one guy is actually just causing a problem, not only that guy, but like it actually drops like all other guys, which is actually very dinky flows. And that is one of the things that we in our network we try to actually fix it. So just.
All right, I'd like to also repeat what everyone is saying. We thank you for doing this work. This is a great start. I'm really wrestling with the metrics, and like, is a low slow start exit good or bad? Is like a high heuristic rate good or bad? And it obviously depends on link conditions, which are unknowable in this kind of experiment. An emulator, it's easy to figure out where the ideal exit point is, and you have no idea. And I keep thinking like, well, if I just straighten the congestion avoidance, like some of these metrics are very good, and that's clearly not. Tells me maybe maybe that's not the way to go. I'm wondering if looking at what happens in congestion avoidance is maybe what you want to see, assuming it's a long-lived enough connection. If congestion avoidance kind of just shoots up in a straight line after that, then you've exited too early. Whereas if you start sawtoothing around the SS thrush point, you've done a good job, like roughly. So maybe that's how you can approach this problem.
Yeah. So we actually do have those metrics sort of in not over time, but sort of like looking at the final congestion window of the connection maybe.
Great.
Unfortunately, those got heavily skewed by all of those low SS thresh losses that we saw, because those also showed up there and were probably not at the right point. And so I don't really trust those for that reason.
Fair enough. I mean, maybe there's a way to filter that data. I mean, you've thought about it more than I have, but thanks.
Yeah. Thank you.
Wonderful. Thank you very much. Yeah, and that could be a good conversation to continue in the hallway as well. All right. Up next, we've got Christian. All right, Christian, I believe you should have slides control, so you should be able to go forwards and backwards. Christian, I see you advanced slides, but we can't see or hear you.
Good morning, folks. I mean,
Good morning.
Gold guys in the early morning are a bit dumb, and they keep being muted when trying to speak. Sorry about that. Now, this is an update on C4. You can look at the updated draft. They are all at the version 4. And you can look at the various simulation source code. They are all on GitHub, so that you can do that. The goals of C4, we presented that last time, is to have a very responsive congestion control algorithm that in particular works well for media applications. And that means media applications have two issues. I mean, if your assessed bandwidth is too small, you are going to not send your video frame fast enough and you will have a bad response time. But if that assessment becomes too large, you are going to send more frames than you should, and you are going to get priority inversions. So basically the idea is to strike a nice balance between the two. So discussions. One of the feedback I got at the last presentation was about the test results. I mean, we are doing our test by running 3,000 different scenarios and running 100 simulations for each scenario. And so the feedback I had was twofold. It says, first, tell us how that compares to classic algorithms like C4 or BBR, like BBR or cubic. And the second was, and give us an idea about the distribution of all the tests. So what I did there is that all those tests are very variable. They depend on minute changes in, say, some random generation somewhere can have very large difference. So now for each test, we present both the average of the 100 runs and the worst 90th percentile of execution times. So that basically, that means that the average tells us how good we are doing on average. The 90th percentile tells us about how we are going statistically in the worst case. It's 90% and not 99% because I'm only doing 100 simulations. In a later phase, when we are really happy with what we have, we could do 1,000 simulation and go to 99% measurements. But now expressing 99% measurement will be completely random. We present those results in the test draft as a series of tables like the one I have here that show that for most tests, the time it took to execute the test, like the simulated time it took to say download 10 megabytes or something like that. All of those are measured in microseconds, and all of those are of the category lower is better. And we did the test by either running C4 as a tested protocol or BBR or cubic so that we can measure the times that we had. I'm happy to report that we are mostly, C4 is doing mostly better than all the competition on all the tests, except just a few, in which case but it's something like 99% better. And I'm happy about that. Now, what did we change? We presented C4 at the last IETF, and we had showed that we had a small, very simple state machine. One of the changes we did was to make that state machine slightly more complicated. The first change is in the startup phases to have a separate state for careful resume. We had implemented the careful resume specification, which is basically you remember the C-wind, the congestion window, and the data rate that you had observed last time on the same connection, and you try to reuse it. That was implemented in a previous draft as some kind of a special condition for the startup. And in fact, what we observe is it's much simpler to debug it if it is a state by itself, and in which we just try those previous conditions. Of course, exit if we do find any kind of congestion, but otherwise start it for 2 RTTs, 1 RTT to observe the data rate. I mean, you can only observe the data at the end of the 2 RTT. And we stay in that condition for 2 RTT because if we exit too early, it does impact performance a lot on satellite networks and similar. So it's both an improvement and a simplification. The second change is kind of related to what Jan and Neil were presenting about the cautionary probing in BBR. C4 by design started by only doing cautionary probing. We call that pushing, but really it was, let's try 1 RTT in which we push at a higher rate, and then after 1 RTT, immediately go back to an assessment phase and wait another RTT to understand whether pushing was successful or not. And the problem with that is that it's very cautious, but it's also very slow. So, for example, if you do that pushing phase every second RTT instead of every RTT, it basically takes you twice longer to recover from a drop in bandwidth and then going to the next bandwidth. So what we did there is the reverse of introducing the cautionary probing, is that say, okay, if we think that the next probing will be successful, then we enter a pushing phase in which we do push at 25% until we don't observe any more data growth or a congestion control event, of course, which gives us an exponential growth similar to BBR. And that makes us much more responsive to say recover to the right bandwidth after an event. So that's one change that we did. The another change was a faster response to persistent congestion. In the first design of C4, we had this idea that, hey, all these measurements are often very noisy. So if we try to just track, for example, the measurement data rate, we let the noise drop that data rate, and then if we drop it, then it will not raise again until another phase, etc. So we say, okay, we will only react to actual congestion event like ECN marks or packet losses or maybe excessive timeouts. But what we observe is that doing that, in the case where we have a link event, like a rerouting event, and the bandwidth of the link drops, it gives us some kind of a staircase. Like, oh, we try for one RTT, we observe a congestion, we drop by 25%. We have another RTT, we observe congestion, we drop by 25%, etc. It gives this staircase that takes several RTTs to adapt to the actual bandwidth that is underlying. So what we change is that, yes, we do this staircase for the first congestion, but if we have two steps back to back, then we say, oh, something has changed. And in that case, instead of just doing this 25% drop, we just align to the latest bandwidth measurement. So that way we drop in 2 RTTs instead of a cascade of 3, 4, 5. And that makes the algorithm much more responsive as well. And finally, the next change we do was for the initial startup. C4 always does pacing. In the initial startup, we were pacing at twice the nominal data rate assessed so far. And what we saw is that gets us in many stuck scenario, in which because that assessed data rate was too slow, it did not increase enough, and because it was the packets were not stand rapidly enough, and basically that was bad for competition in a number of scenarios. So the solution was to put the floor on the pacing. It's basically, at least during slow start, don't try to pace at too low a rate. And the sending will still be limited. It will be limited by the value of the congestion window. But the pacing will allow, say, packet trains to go out, etc. And it will be much more robust. For example, if the RTT is smaller than what you have measured so far.
We're bumping up against time, so let's keep moving.
Okay, and so we try multiple values, but basically we pick the smaller one that we tried. We pick pacing doing so at least 1 megabit per second to not get stuck. And it does remove the getting stuck conditions, and it does improve performance overall. So where are we? Well, we are at a point where the results are pretty good. As I say, we can look at the test result, and for all the scenarios that we measure, we are happy with what C4 does. we either need to add a couple more scenarios. We need to add a cellular network simulation to our simulations, so that basically we can measure what happens when your bandwidth and data rate are constantly changing. We have done an ECS simulation. We probably need to add RED and RED ECN simulations as well, because they are things. We have in the simulation a limit on the bandwidth. I mean, the buffer buffer in the routers are set typically to 2 BDPs, sometimes 4. That is not quite testing buffer bloat. We need to have a test case in which the buffer are something like 20 times BDP and see what happens. We know we have to drive down the latency in compete scenarios. Currently in compete scenarios, we get to reasonably fair sharing between connections, but that fair sharing is driven by connections backing off in case of congestion. And that means that if we do not have congestion, I mean, that means that basically they get to the equilibrium by pushing the network to the congested state and having long delays, at least 1 BDP of delay. I would like to fix that. It's hard to do. It's impossible to do when competing with cubic, because cubic will not stop. But in case of competing with congestion control that do measure the data rate and things like that, it should be possible. So that'll be my next effort. And we are starting to deploy in real test, not just simulation, but we need that to experiment from live networks. And that's what I have.
Thank you, Christian. I think we've got Neil in the queue for a very quick comment.
Given the time, that's fine. I'll do it over chat. Thanks.
Sounds good. All right. Thank you all very much, and we will see you on the list.